Hello, let us have another example. Now we define the expected value for discrete type random variable. So suppose that the PDF of a discrete type random variable is given to us by its probability density function. So this probability density function basically means that we have a discrete type random variable. So at point xi, I have a probability mass of pi. Okay, so let's say this is x1, this is x2, and this is, let's say, x4, etc. And then you have different probability masses. So this is P4 and so on. So obviously summation of PI's, which are real numbers, should be equal to 1, and PI's should be all non-negative, and I equal to 1 to plus infinity. So you remember that the number of discrete points on x-axis, where you have masses of probability, they are countable. So how we define the expected value of this random variable, or mean of this random variable, is same as before. Expected value of x is always equal to integral. This integral means summation of all values that x can take on, and then the times probability. So this means that what values x can take on, the values that x can take on is x1, it could be xi, and I could be equal to 1 to plus infinity and times probability pi. So basically, this is the definition of expected value of a discrete type random variable. Means the location of mass times, this is the mass of probability, times probability mass. So using probability mass function, we can quickly calculate the expected value. So this is general definition using Riemannian integral, and then it is equal to integral from minus infinity to plus infinity of x times fx. I substitute, so I will get a summation of over I equal, let's say, 1 to plus infinity, whatever it is, and then pi and delta of x minus xi, and then dx. Now I could change the order of, because integral is basically a summation, I could change the order. I could put x inside there, so I get integral of summation of xpi delta of x minus xi, and then dx, and then here I equal to 1 to plus infinity, and from minus infinity to plus infinity. So these two, I can change the order. Moreover, if you multiply delta of, let's say, x minus a times any function g of x, this is always equal to delta of x minus a. This is always equal to that, and GA. The reason for this equality is that this function is 0 everywhere except point A. So this function is also 0 everywhere except point A. So the only location where both sides of this inequality are non-zero is at point A. At point A, both sides of this equality, if you put this xa, I get exactly replica of that. And if x is not equal a, both sides are 0. So this equality is 0. So what I could do is that, because I have this xi, I could put this xi instead of this x. So this will become integral from minus infinity to plus infinity of summation of xi pi I equal let's say 1 to plus infinity of delta of x minus xi, and then dx. Obviously, this is constant. This is not function of x. I could take it out of the integration. Okay, so in that case, I get summation of I equal 1 to plus infinity xi pi, and then I get one integral of delta of x minus xi, and then dx, and from minus infinity to plus infinity. And based on what you know about delta function, this integral should be equal to 1. Okay, so this will become summation of xi pi I equal 1 to infinity. So this is same as what we calculated using the Lobeck integral. So obviously you could say that if you have a discrete type random variable, you multiply the masses of probability by the location where the mass is located, then you get the expected value. So the point mass, this is the probability mass function at the distance of xk from the origin has a moment of this one. So this is why we call this a moment, because in physics, if you have a mass here at this point, pi, okay, if this is the mass of pi is at this location and this distance is, let's say, xi times pi is a moment, this moment, and the total moment is summation of all the moments. Okay, so this expected value is the total moment of your random variable. This is why expected value is a moment of the random variable. It's the moment of the random variable x. Is the mean of random variable x. So this is why we are using different terminology for the same thing. So the total moment of all point masses is expected value, or so on. And the total moment in physics represent the center location of the mass. So is the center of the distribution, center location, mass of the distribution. So the mass distribution of a random variable is centered at the expected value. So it is physically meaningful, particularly given that the total probability mass is equal to 1. So this is why expected value is referred to the center of the probability mass function, in general, the center of the distribution. So let us have one example, which is the mean of a geometric random variable.